So welcome to the workshop on T-ray, metrology, nanometrology. Today, we are discussing mostly about the user manual, because the user manual walks you through the procedure that we adopt for imaging. And there is another part for spectroscopy. So this is one of the one of the orientation of the machine or configuration, if you want to call that way. This is a free space version, and there's another version that's fiber coupled. As this image shows, there is a x-axis, there is a y-axis, and there is a z-axis. And the box behind, and this is actually the round thing, is the sample or wafer. It's not showing very bright here. But behind that is the main box, which houses all the, the source, the detector, everything in there. And the box itself is fitted with a vertical positioning stage. So the purpose of this vertical positioning stage is that you can lift the box up and down and fix it at a certain height. And what it helps is that, let's say, imagine that this is a 100 millimeter wafer sample. In that case, then, the beam has to be initially, before we start scanning, the beam has to be at about the center of the wafer. And how we know that? We do an X scan. Box is not moving, wafer is moving, right? So we bring the on one side, the wafer bring on one side, then do the scan on the x-axis and figure out where the center is, and do the same for y-axis. So
are we moving the wafer like only on the X side, or we can move it like
on X, Y, and Z, on all three axes? So because we want to scan, let's say for this, if this is a 100 millimeter wafer, then we want to scan 100 by 100 area. Whatever depth is very minimal. If we scan in the depth, we hardly ever scan. We need to scan 1 millimeter. We don't need that. So a lot of times it's in the microns, right? So in case of 100 millimeter wafer, if I had a 200 millimeter wafer, then obviously the box need to be repositioned to get the whole 200 by 200 area. That's the purpose of this vertical positioning system or stage. So that it can accommodate a bigger sample, it can accommodate a smaller sample. For a smaller sample, we don't have to worry much, as long as the beam is on the sample. And where is the beam? It's easy to find out, because we have, let's go to the next slide. I will show you. So this table of content, the overview. I'm sending this manual to you so that you guys can read it. Maybe I should send it right now. So let me stop recording for a moment, or actually pause. Okay. So as you can see, the system has three main components. One is the main box or main unit, as we call it, TN3DI, terahertz nanoscanning 3D imaging system. And then there's the main box and the nanoscanner, which has the X, Y, and Z stages or positioning system. And then, of course, you need the computer and all other hardware to get the scanning and imaging done. So the components and diagram of the system is, we showed this before, that, the main system is, the box is the main system A, and then the B is the nanoscanner, and everything else is computers and digitizers and all of those things. But these two are the main system. So basically, the nanoscanner is holding this sample from the box. The T-ray beam is coming and hitting the sample and then going back into the box for detection. An example is here, as you can see, is a sample mounted on the nanoscanner. The box is behind it, not very much visible. So the beam comes from, the hidden side, goes back into the box. And because it moves around, therefore the whole sample is scanned. This is a smaller scanner. This is a 100 millimeter by 100 millimeter scanner. And there is a 200 millimeter by 200 millimeter scanner. And we are making the 300 millimeter scanner now. We are in the process of making that one. So these are the off-the-shelf digitizer that we use, and also a power meter. Power meter is not essential because you can calibrate the detector with respect to the power from voltage reading. But we use this is a very standard Newport power meter. So we use that to, have a visual reading as well as we can record it. So as you can see, the power meter and the digitizer or DMM has three different interfaces: the GPIB, the Ethernet, and then USB. Sometimes all of those interfaces are used, sometimes only one or two used, but other interface is needed, as you can see, for the nanoscanner, because the nanoscanner has three axes, X, Y, and Z. So those are also connected to the computer by not COM3, but USB. COM was older version, and now everything is on USB. Once those are done, then, and the system is installed by, by us, and training is done. Then these are all the softwares that are installed or pre-installed. And so you know that if anybody asks you, if a customer buys this system, all the software licenses are bought in their name. So they have all this software in perpetuity on the system, and it's there. And then the hardware setup, etc., not much there. And last time I had showed a little bit, but this is how the interface look like. On the V, what is they call Agilent V? Now it is Keysight V. So several apps that have been developed for the complete operation of the system. This one, what we call is the XYZ positioning, that runs the nanoscanner interface. And the purpose of this one is that all of the stages on the nanoscanner need to be, when you start at first, they need to be homed. There's a home control here, and then you can move them anywhere within their range. So when you run it first here, these 3 boxes will populate its current position. You can home them, then it will go to 0, and you can move them anywhere. This is frequently needed, actually. It's not just, for example, you use the interface to figure out where do you want to scan, let's say on the x-axis, right? Then the markers, you can see that tells the user its current position. One marker here, one marker there would tell you where the start and where the end is. And these numbers, then you can put into the final scanning program. I'll show you that. So then it means that if this is the starting point, then x-axis should be at the starting point, right? How do you make sure of that? You use this interface, like I showed, this one. Multiple windows are open all the time. So then you can put that number in the X box, click on OK, and it will go there. And it does it every time without failure, right? Otherwise, the machine would not function. Similarly for y-axis and similarly for the z-axis. So here is the Y scan, and then you can pick up those numbers and put it in the final scanner. And similarly for z-axis, because what happens is when G is at the end of its travel, which is closest to the sample, that doesn't mean that the beam is focused on the surface. So what we do a Z-scan to figure out where the beam is focused. So for example, this diagram shows that this is where the closest point to the, end of the travel of the G stays, which is close to the sample at the end. But as you keep pulling the stage away from the sample, maximum intensity is here. So that means this is the focal point on this surface. So these numbers, then you can put it in the scanner as well. When we do all these, these are the preparations that we need. Once the preparation is done, meaning figuring out start and end of the X and Y and Z, then this is the main scanner. In this scanner, you see this is the x-axis. So we have the start and end. This is y-axis, we have the start and end. And this is the z-axis, we have start and end. Now on x-axis, the scanning is continuous and data are streamed. That way, it's a little bit more efficient. It's not just go there, get the data, go there, it's not that. The stage keeps streaming and the mechanism keeps reading the current position, which is pretty useful because otherwise it would take even very longer.
Uncle, how do you get to this conclusion about the x-axis that it's continuous?
Say that again, sorry, I didn't.
How did you get to the conclusion that how is it on the x-axis?
Okay, so that's sample dependent. That you would not know ahead of time, right? If it is a wafer, then you have, there are many strategies that an experimentalist need to deploy. So let's say I have a film, thin film, for example. And that thin film is on some kind of substrate. And let's say film does not cover the entirety of the substrate. If you do an X-axis scan like here, as we showed, if you do an X-axis scan, this is Z-axis, but let's say this was X-axis scan, then it will show the start and end of the feature that you're doing. And then you can pick up that number and put it in the scanner, right? So let's say, let me give you another example. Actually, this one probably a better example. So if I start, you see when the beam is not hitting anything, right? Then the intensity is very low, close to zero. But as soon as the sample hits the beam, the intensity goes up. And according to the feature of the surface, the intensity will show the feature, and when the sample ends, it ends. So if I have a film on a substrate, a lot of times that is the case, then the shape of the scanned profile will show you where the start and end of the sample. And then a lot of times what one needs to do is first do a rough scan and get a rough image. But even though rough image, it will show features. And when you want to inspect a feature more closely, then we can do a fine scan. A lot of times it is done that way. But again, the basic scanning steps are always this way, that you figure out where to scan, put those numbers in these boxes, also give a file name so that data are stored in that file. Then you can control the scanning speed. In fact, the X-axis resolution, if you will, is controlled by the scanning speed. Higher the scanning speed, lower the resolution, meaning that bigger the difference, right? Points are far away. Lower the scanning speed, closer the points. More closer the points, better the measurement. But there's a trade-off, because in some cases, we don't need to get so fine resolution, but in some cases we do need. So we have a tremendous range. This positioning systems, we can scan from 500 nanometer per second all the way up to 10 millimeter per second. So if we are scanning 500 nanometer per second, and you are getting about 200 data points per second into the computer, so your resolution 500 nanometer divided by 200, that is the hardware resolution. But if you are scanning faster, then let's say you're scanning 1 millimeter per second. So now you have 200 points within 1 millimeter, as opposed to 200 points within half a micron. You see the tremendous difference between the scanning resolution. So like I said last time, the 3-factor determines the image resolution. One is the scanning resolution, the other one is the gridding resolution, and third one is the rendering resolution. And I will show you all of those things. So, with that, let's see what else. You have the whole manual. There may be some mistakes in there. So read it, and if you find any typo or something wrong, please let me know so that we can correct it. And believe it or not, this manual was written by an intern in my lab. So the young people are very smart, and they are doing a fantastic job. So here is another. You see, this is a hard disk plater I showed before. We took one of the, we broke one of the hard disks that didn't function anymore. And it took that disk out of it, mounted on the nanoscanner. You saw that picture before, and then wanted to get image of it, right? So we scanned. This is how the, everything when it's scanned done, this is how the intensity profile look like. Of course, there are so many scans here, right? So one on top of another, nothing can be understood.
The intensity is normalized to the max wave?
No, you could do that, but that's not necessary.
Okay.
In other words, for imaging, the intensity, is the shape dependent intensity. So whether we normalize it or not, we'll get the same image. Some sharpness may become a factor at some point of time, but in most cases that is not an issue. So, but we have never tried to normalize it except in spectroscopy. In imaging, we did not need to. We have not tried that route. We didn't need it, so to speak, because as you can see, when the imaging, this is the intensity that is recorded, and then the image is generated from that intensity. And you can rotate, you can, turn around, see upside down, etc., etc. And all nooks and crannies can be become visible. And then, if we want to characterize the surface, then then this image is loaded into another software, and probably you should do a practical example of that. And depending on where you draw the line, this surface, characteristic comes on the screen, and then you can calculate the roughness parameter from this kind of plot. So this, as you can see, this is a 100 millimeter, almost 100, yeah, it's about 100 millimeter diameter disk. It's a big sample. In a lot of cases, the samples are going to be a few micron. And you have a lot of control on that as well. And so this part starts to show you the imaging. The software we use for imaging is called Voxler. Then that is loaded, and that reads in the data file, and then it it can. And so this is how the interface is there. You can choose what data file you want to image, and then it will read that data file. This is how it looks like when it loads the data file, because the numbers are automatically sorted with the parameters you choose here. But these are all pre-selected, so it's pretty easy to use. All you have to do is when the data file is loaded, you click on OK. It loads, and then empty screen comes in, and then the first thing we do, we connect a grider to the data file. So you get this window or interface. The data file is shown here. As long as data file is highlighted, then all the math and plotting stuffs are here in what they call the module manager. So they have a module manager, they have a network manager, they have a property manager, and then the display window. They are the four main components, but there are many more. So we first load the data, then bring the grider, connect the grider to the data file, and then we don't have to, we have a lot of leverage here. If we want to image the entire thing, then this window is not all that important except for the resolution. This is what we call gridding resolution. All right, because the resolution is by default 50 by 50 by 50. That means 50 slices along x-axis, 50 slices along y-axis, and 50 slices along z-axis. A lot of times we don't need that, or a lot of times we need more, and sometimes we need less. How? For example, we changed these parameters for, let's see if there is an example of, right, it is not example. But let's say we didn't change any parameters, then we get a coarse image, something like this. So as I showed before, as we gradually increase this the grading resolution, the image becomes, I don't know if you can still see it, but as you see, coarse, finer and finer. That means more number of slices you make in the grading option, better is the image. There's no limit for it except for the whatever is permissible by the computer memory. So other than that, theoretically, there is no limit. And then if so this is the, this is the image, something like an SEM or a AFM would produce. Now, if we want to go to lattice resolution imaging, then some consideration must be taken into account. One is the scanning volume. Lattice resolution scanning volume probably would be 5 micron to 10 micron by 10 micron by 10 micron. And then the grading resolution has to be much higher. This is a different issue. I'll come later. But the graphics modules are, these are the graphics modules. There are so many different kind of graphing that can be done. It's not all of them are the same. So the contour plots, you are familiar with the contour plots, face rendering, height field, isosurface, oblique image, ortho image, scatter plot, streamlines, vector plot, wall render. So common surface is done by height field, which is regular imaging technique. Scatter plot is just the data. It plots like the XY plot in Excel. So that's a scatter plot, meaning X versus Y plot, nothing else. Then the vector plot, of course, depends on the direction, and the wall render is produce the volume image. And the spatial imaging, isosurface, oblique image, ortho image, those are very special kind of imaging. Isosurface is an important aspect. I'm going to show you a practical example of that. Isosurface is a, are you familiar with contour plot, right? I presume you're familiar with contour plot. Now imagine that, let's say you have a mountain and you are plotting the contours, right? Contour meaning that those are the part in the same height. Now you want to see that in that volume, how does it look like in 3D? You wish that you could extend the contour inside the surface and see the whole volume. If you do wish that, that's what it provides, the isosurface. It provides a three-dimensional feature of a volume image where the materials are the same. So, it looks very, I'll show you an example so that you can understand better. So for example, this is a volume image. This is a very special sample that we got from a government laboratory.
I have a question.
Yeah, sure.
Does on the previous slide, the one you said, so is it like it takes the images of isotopes? Isosurface?
Isosurface is no, so isotope is a nuclear phenomenon, right? Isotope is a different mass number for the same element. That's isotope. For example, carbon 13, carbon 14, carbon 12, right? This carbon same atom, but it has different mass number. That's why they are called isotope.
Yeah.
The word isosurface, I think it's something similar to identical. And just keep that thought in your mind. I'm going to show you a real example, then it will be clear, right?
Okay.
Keep it in your mind.
Okay.
Let me, yeah, we're almost towards the end. So the volume image, is, and I will show the ISO image of this one, as you will see. So remember this image. What are these? This is ionic liquid polymer, or they call polymeric ionic liquid. And those are the matrix. And in the middle, those little dot-like things, like here, you can see that those are quantum dots. So what they did is they made a composite where quantum dots are surrounded by the ionic polymers. And this is from Los Alamos National Laboratory. So they are the one who, here's the reference, as you can see. So what happened is they did the X-ray scattering, small angle scattering, and all of those things. And they didn't have any visual confirmation that what they are doing. So this provides the visual confirmation. But the point is that, this is a silicon carbide surface. Okay, so this is, you see this pretty picture. This is a drop of nanocellulose on a silicon wafer and let it dry. And then we imaged it. And this is not very high resolution. But you see, when you take the contour plot of that, this is the contour plot. Then this is how it looks like. But the isosurface plot, you see this mountain-like thing or caldera-like thing that happened in a few microns of space, that is captured here. I mean, this, this thing, it changes, of course, based on the ISO value. So you can inspect, when you can superimpose this onto that image, and you can see where is this feature is from. In other words, how is the material distributed in that part of the sample? I'm not going to go to electrical characterization today. I'm going to show you a little bit of this. So let me load an image. I would like to find that plater that I have shown you, or anything that we have in there. So you see, this is our image processor, right? And can you see it?
Yeah.
Good. So first thing we do is read the data. And in data, I think we have hard disk plater somewhere. There we go. Excuse me. So all data file has txt extension. or file extension. So you see the data files are named in a way we know what was the x-axis speed. Here we scanned it at 7 millimeter per second or 8 millimeter per second, but some cases we scanned 2 millimeter per second, for example, this one. And as you can see, the data file size, lower the speed for the same area, higher the data file size. So if we load this one, let's see how does that look. And all we have to say is say okay, and the data are loaded, still reading. So this is a pretty graphics intensive, and this computer doesn't have a very smart graphics card, but all the systems, they always come with pretty high-end graphics ability. I don't know if you can see that yellow dot here.
Yeah.
It means something going on. Still have not done reading, finished reading all the data point. But we can now connect, you see that grider here, right? So our first thing is to connect the grider to the data point. We can do it either pulling it here or just double clicking on it. As long as this was chosen, double click automatically connects it. If it did not, let's say, if it did not, then we can of course bring the grider here and then connect it ourselves. The same. The grider is the one that creates that prepares the image for generation. How does it do that? It has, you see the property manager box here that has the general thing here, geometry, and there is search function that you can search for a specific value. But the geometry shows you from where to where the x is going to be measured, the y limits, meaning that start and end of y, and z limits. G has some value here, but probably there's artificial. And then the resolution. So X is telling you the scan started at 0 and went to 100,000 micron. Y is 0 to 100,000 micron. Z or Z axis has, few micron of scan, but it's not very important in this case. And also you can look at here, it has the ability to look at the data file. If you go to it, click on the data file, edit worksheet, and so you can see the X, Y, and Z values. G started at 25.4 millimeter. Oh yeah, see it went down. So this is a actually three-dimensional scanning. So it went down to 25.16 millimeter. So that means the grider shows us the geometry that we're seeing is right. Now, what we can do here is this resolution and spacing, they are related, meaning that I have now 50 slices along X, 50 slices along Y, and 50 slices along Z. But if we want to have equal spacing of all the slices, right? And of course, you see the X spacing is 2040 micron, and that's very high. So we can bring it closer. Let's say we make it 500. You see, when I made it 500, the NX went to 201 instead of 50. And I can make 500 here. and then NY changes. And if I cannot make 500 here because I even don't have 500 micron scan, right? But also I don't want to 50 slices in the 160 micron scan that I have. So I can change that either here or here. Either way is fine. So let's say we want, we can keep 50 slices, but for now, let's say we want only 10 slices. So then this spacing number automatically changes. If we make it a round number, let's say 25, then we have 11 slices. And then we go back and begin grading. So as we begin grading, it's gonna take a few minutes. As you can see now, the grading is progressing. This is the time-consuming part of image generation. And this time takes longer if you saw that number of slices, right? More number of slices, longer it will take. Less number of slices, shorter it will take. Okay, so now the grading is done, and we're ready for looking at the images. So as I said, height field is one of the common mode of imaging. So this is the platter, you know, and it has a hole in the middle. That's by design. But as you can see, as we have scanned, the hole also have certain thing. Whether they're real or not, we can figure that out. We can do analysis on that. But certainly there's a defect here, and there are more defects. There are more than one way of zooming it, but as you can see, some surface roughness is now visible, right, on the screen. And this will be finer if you do change the grading parameter. Instead of 200, if you make it 300, for example, and whatever the numbers are you see they are changing from 500 to 334, etc. If we keep the z-axis the same way, notice what happens. So we'll begin grading again. Are you able to see the surface roughness here visually?
Yeah.
Now, if we do begin the grading, it will take several minutes, but let it finish and you'll see those dots are coming closer, the surface roughness.
How do we know that which parameter we have to change to get a more good texture?
It depends on the sample. It depends on the objective of what you want to do. Meaning that what are we trying to get from these measurements? Again, this is a metrology. So metrology means the science of measurement, right? So any imaging that we're doing, why are we doing this imaging? Because we want to measure the properties, features, or be it surface, be it volume, etc. So now you can see that this is how it is looking like. And then with height field, as I said, we made 11 slices. Not all slices would look the same. So this is the slice number 11. And as you see, as you go to this slice number 1. So the features are slightly different. And then you can analyze all of them one at a time or at a time. But it gives you the tool that what's at the depth, and the surface, it may look like this, but when you go a little bit at the 160 micron deeper, they are changing. So it's not always the same. And then what we can do is we can take this image and also do other. First of all, let me show you. A grayscale image is not only thing, right? We have so many ways of rendering this. We can make it different color. Whatever, it doesn't change the image. It doesn't change the properties, but some samples look in a different way better than, purely grayscale, for example. So, and we have that option here. So you can spend your day and night, figuring things out, for example. So if we go back to the grayscale, and we can take this image and measure its parameter. And question is, how big of this defect here, the thing, like hole-like thing that's looking here, are they big? How big? Why did that happen, etc. So this tool then can help. What we can do is take this image, let's say, I'm gonna save this image as we usually go to JPEG, but you see all different kind of formats are available here. BMP, PSGIF, IB, JPEG different kind, PDF, PNG, etc., etc. All the common formats are available. TIFF. So let's call it workshop 1 JPG, because we're going to JPEG image. And we save, then it comes here and asks you how many pixels you want. So it's, not necessarily 100 megapixel, meaning 10,000 by or whatever the number is. You can control a lot of other things, and it depends only on computer memory. There is no, program doesn't limit anything. So, and then we are having pixels per inch is 2400, but you can have 600, you can have more or less, whatever. You can have color depth. You can also, in this case, because we took grayscale, color depth is not changing. A comfortable is 8192, that many pixels, by that many pixels. So that means how many pixels altogether? If you multiply 8192 by 6826, then we get 55.9 megapixel. But you can always change that, right? And the second number, the width and height, is when you say the maintain aspect ratio, then it's maintaining the aspect ratio. And if I say yes or okay, so that image is saved. And then we want to measure the surface properties. Then we go to this other software, which is called Image J. This is a free software that NIH created many years ago. They are available freely for everybody on the internet. And we use it because of capabilities it has is really unparalleled. So now we can open that image. It has to go, it went to HDD platter, this one, and the W1. And so what we can do with this image now is we can do all different kind of analysis. For example, surface roughness, like I showed. So the key is to first set the scale. And we know that from one end to the other end, this is 100 millimeter. So we go to set scale, and then known distance is 100 millimeter. 100 unit is millimeter. And once we set that scale, then what we can do is we can look at the surface roughness, for example, via called plot profile. So let me bring this on this side. So what is it doing is it's assigning brightest or whitest part 250 pixel, and black is 0. So if we want to avoid this one, let's say we want to measure how thick, how big is this. You see now this is in scale. The x-axis is 100 millimeter. And what is the defect? Then if we draw a line, we have to go to line mode. So you see now it is defect starts here, ends there. So it's about, you can now measure the cursor read over here. So at this point, X is 8.57. Over here, roughly about 0.79. So this thing is about 8 millimeter. So let's say, that's the information that someone can use. If I want to know what is this one over here, then I have to draw over here, and I can move it around and see any place I want, and then measure. And if we bring it on the surface, although it looks pristine surface, but it's not all that pristine, as you can see. Somewhere else is probably, but so what happened is it didn't go all the way to the 0, so it looks jagged like that. But let's draw another line from there to there, and we can go to fix the scale. How do they do that? I know it is doable. Is set range. Yeah. Y from, so Y mean, we can call it 0. And that way, but you didn't have to, or we didn't have to. But the kind of thing can be done. I can draw the line anywhere else and see how the surface properties, etc. So you get the idea. Any question up until now? I know there are a lot of questions, but that's okay. It takes a little while to sink in, which is okay. All right, so what you will have to do is I'm going to send you a link for this ImageJ software. And I will send you some image so that you guys can play on your end. You guys, you can do that, right? You have computer to download and install that software. So you'll be able to. Maybe this particular image and calculate the surface roughness. Is there something you would like to do?
Yeah.
Okay. All right. So let me save this image. Save as JPEG.
One question about sample quality. Temperature plays a factor in certain samples with specific impedances. How much of an influence is temperature or humidity to the sample?
It totally dependent on sample. So
Okay.
it's very critical for semiconductors. Semiconductor is very sensitive to temperature.
Yeah.
And the T-ray reflection is also sensitive to temperature, sample temperature. So in other words, you could easily make a temperature sensor with this thing. Or even there are other applications of remote sensing that we haven't talked about yet. Big structure or small structure from distance, you can shoot a T-ray beam. It comes back to your detector. You can sense the vibration and those kind of thing, the remote sensing, just like you can do the temperature sensing as well. So
Okay.
in the laboratory conditions, the temperature is very well maintained. But still, if there is any variation in temperature, that will show in the profile as well.
Okay.
And vibration, of course, is also sensitive to vibration. So, and some samples will be sensitive to moisture as well. So humidity could be a factor.
Thank you.
Those are the kind of things that experimentalists will always be mindful of.
Mhm.
That's a good, very good question. Anything else at this point? So let me save this as a JPEG file. Actually, we already have a JPEG file, so I don't have to save it. Don't save. So I'm gonna stop share here, and any other points to quickly discuss today? All right. So let's stop here for today, and next week I'm here. The week of the following week I will not be here, but maybe that will be a good time for you to do a little bit of project if you wish to do that. So if you wish to discuss a topic, that would be fine. You may want to send me one paragraph of your idea or something. If you wish to, we can already discuss. So let us stop recording today, and